last talk and discussion for this morning is by Thomas Andrillon. He says Tsuchiya because he was a postdoc and he is now a postdoc in my lab, but he got the NHMRC ECF, so he's becoming independent from this fall. And now, two prominent philosophers from Monash arrived, Jakob and Tim, so now it's becoming quite interdisciplinary, interesting, even more. Okay, go ahead.
Can you hear me?
Yeah.
Well, I'm still part of NOW's lab, so I'm trying to enjoy both the joy of independence and having someone caring of the not so joyful stuff of science. I will try to keep in the sweet spots for as long as I can. So I will present here a very brief overview about why is it interesting to study sleep to understand consciousness. So both things, old and new, of what I did and done by others. So I'm sure that you're all familiar with this enigmatic figure, showing that consciousness can be mapped along two main dimensions. One that is a level of consciousness, so whether you are in a state that allows you to be conscious of something. So consciousness in the intransitive sense, in a way, and one axis that is the content of consciousness, so being conscious of something. And you can see that with these two dimensions, you have a very different state that can be mapped out. And the advantage of sleep is that you can have access to both modulation on the level axis and on the content axis. Because in some parts of sleep, you will be in a state of unconsciousness, so reduced content and level, and in some other parts of sleep, you will still be at a very low level of arousal, but still be able to maintain some conscious content, such as when we are dreaming. So sleep, in that sense, has allowed to tackle some of the important questions about consciousness. One of the first one, I think, is regarding the level. And first question that was tried to be answered is why consciousness fades during sleep. So why do we lose consciousness when we fall asleep, which is an experience that we all can experience pretty much. So that's what the work done by Giulio Tononi and Marcello Massimini when Marcello was working with Giulio in Wisconsin. So they used something that now already mentioned, this TMS-EEG experiment. So you perturb the brain and you look at how the effect of this perturbation. So in a way, it's a bit like throwing stone in a pond. If you want to know if the pond is frozen or not, instead of stepping on it, you can just throw a stone. And if you have ripples, usually it means it's liquid, and if you don't have, it means it's solid. So it's a bit a similar approach. You throw a stone in the pond. Here the pond is a TMS pulse, and you examine the ripples. And what you can see from that graph is that in wakefulness, these perturbations are characterized in two ways. They're extended in space and in time. Where the non-REM sleep, although initially they are of a higher amplitude, they seem restricted in time, so they stay close to the stimulation points, and they also vanish more rapidly. So it seems that the loss of consciousness is associated with this loss of cortical-cortical connectivity. So signal will have a harder time to travel in the brain. And this is an artificial signal. It's perturbation that had nothing to do with regular functioning. So that's really was one of the founding, I think, arguments for IIT, putting the stress on the need for integration in the brain for consciousness. And as Now was mentioning, this was formalized or quantified recently with this PCI value, so this perturbational complexity index. That showed that indeed complexity of response to perturbation do not only allow to identify moments of consciousness during sleep. So you can see that although there are completely different states physiologically speaking, wake and REM both rank high in this PCI value, where deep sleep, where usually people are unconscious, rank low. But this seems to be something that works in sleep, but also in other states like anesthesia or brain damage patients. Another question that can be answered through sleep is a reverse question. Not only why consciousness fades during sleep, but why also it reappears during sleep. And in that case, it will be why suddenly we can start dreaming while we're asleep. So it has been presented as some sort of brain in a vat. So your brain is isolated from the environment, and suddenly we generate conscious contents. And how it can do that. So there have been several accounts for this. A lot of the literature has focused on the link between REM sleep and dreaming, and trying to find in the physiological basis of REM sleep a base for dreaming and therefore consciousness. But recently, all of this literature has been a bit transformed because people started to remember that dreaming is far from being present only in REM sleep. We dream pretty much throughout the night. It's just that dreams tend to be more numerous, more frequent, and more bizarre in REM sleep. So we tend to remember more of these dreams, but they are actually also present in parts of non-REM sleep. So if you want a neural correlate of consciousness, for example, you need a correlate that will be state independent, that will be the same whatever state you are in. And that's pretty much what Francesca Siglari, so when she was working with Giulio Tunoni in Wisconsin, reported by showing that conscious thoughts in sleep, both in non-REM and REM, were associated with the same signature. So an activation in the posterior, the central parietal cortex that is activated when people are reporting conscious experience. And very interestingly, they, yeah.
So Thomas, could you just say how they measured the experience in non-REM sleep?
So in a very simple way, they just wake up people.
Okay.
So they have these very long repetitive nights where people come for naps or nights, and then they just wake them up and ask them. So sometimes it conflates the point of memory, and they looked, I didn't put it here, but they looked also at when cases where people say they were dreaming, but they cannot recall what exactly. So they still have the same activation pattern. It's actually even more posterior. So when they cannot recall, the bits of frontal activation that you can see here vanishes. And their argument is that the frontal activation are really related to your ability to remember and report, while if you're just conscious but you don't exactly know of what, you will have only these posterior activations. They also find in wakefulness. So this is a contrast with intensity of thoughts. So same thing, people are doing nothing and interrupted from time to time. And the more their consciousness was rich in a way, the more you have activation in these central parietal regions. Yeah.
That previous slide, is that directly contradicting the earlier one you showed, or that was PCI? Is this PCI as well?
No, that's a more simple contrast of activation of sources.
Just EEG?
Yeah, just EEG.
And did they talk about, I mean, is it right though that it is directly contradicting the work of the same group with the PCI, showing the differentiation between REM sleep and the non-REM sleep?
Well, no, not exactly, because so here non-REM will be the part of non-REM in which you are conscious that will show this pattern activation. But generally speaking, your level of consciousness is quite reduced. So it's more in non-REM sleep, and actually here they put everything, so the deepest and the lightest part of non-REM sleep. Sometimes you can be conscious. And
so this is only data from moments where they woke people up and they said, yes, I was conscious.
yeah, contrast is when they were saying no.
Okay. But when they're saying no is not there.
So it's a contrast. The T-score is between the two. So basically, when in a state when you're conscious, you will have this pattern of activation in the part of the brain, but the baseline will change from state to state. So if you compute the PCI on average, in non-REM sleep, it's pretty low, but it doesn't exclude the fact that sometimes it can go a bit higher.
And the dream content during non-REM is also really reduced, right?
Yeah, it's usually simpler and it doesn't have a scenario. It's more so So maybe it's also why it's harder to pick, because you have to interpret really at the right moment. Yeah.
Is the take home from those two sets of 4 images that they overlap? Because I don't really see that.
So remember, it's CalVG, so in terms of spatial precision, we can be a bit more inclusive. But yeah, the idea is that they overlap. So here you're missing actually one of the 3 graphs, which is the one where they don't have recall of the content exactly. And when you map all the 3, you have actually a central overlap that is pretty much here. So there is a common core, but then of course it can be more or less extended.
Thomas, one more thing. Is it fair to show the medial aspects of the cortex in that way when it's an EEG measure?
Pardon?
Do you think it's fair to show these differences on the medial aspect of the cortex when it's a scalp EEG measure?
So yeah, so that's the problem of source reconstruction, is that it's full of priors, and it, yeah, maybe with a different method of parameters you will obtain a map that is quite different. And this paper has triggered a lot of discussion.
Well, it's also important to say that this one actually uses a 256 channel EEG.
It actually removes most of the subcortical.
Right.
Where you see
Yeah.
the black stuff. So,
Yeah, but it's true that they still interpret activation in the midline that is, yeah, not necessarily the most easiest to pick. So it's loaded with assumption here. So yeah, so just to for this question of level, this work seems to mean that consciousness is characterized by differentiation and integration of activity, but for a brain to be conscious, it doesn't need to be, apparently, according to this result, differentiated and integrated anywhere. It seems that you have a sufficient set of region, the posterior region, that are sufficient for consciousness, while frontal activation has been mostly associated to reports. So that's fueling in this debate between is consciousness a frontal parietal thing or a parietal thing only. Another way of using sleep to explore consciousness is looking this time at the level of the content, and the kind of thing I've been doing when I was working with Sid in Paris. So we used sleep as a modulation of the level, and inside the level we're looking at what kind of content can be processed. So typical experiments look like this. You have people doing simple tasks while falling asleep. Stimulation continues during sleep, and we look whether processes are continued and maintained during sleep. Since obviously you don't have any behavioral response because people are falling asleep, and it's in a way, the way we define sleep is because they are still responding and they have a pattern of activity that corresponds to sleep. You need a marker, an electroencephalographical marker of their ability to do the processing of the stimulus. So in this first set of experimental markers was motor responses. So stimuli categories were mapped to a side of response, either right or left. The good thing about this is when you want to respond right, you have a pattern of activity and a lateralized response to the contralateral hemisphere that you can track with EEG. So our goal here was to see whether, if you are asked to categorize stimuli during wake and this task continues throughout sleep, whether you will be able to continue this categorization while sleeping. And this is the kind of result we obtained. So we obtained the same result in 3 independent experiments, so we're pretty confident about it. What we obtained is patterns of lateralization after stimulus onset that is delayed in sleep, but a delay that roughly corresponds to the kind of slow response you give when you're drowsy. So it seems that even here the task is quite complex, classification of words based on their meaning. This is the kind of thing that in light sleep is still able to continue, pointing perhaps to the fact that a lot of processes can be maintained without us being aware or conscious of it. What we did also was to try to predict the maintenance of sensory processing using this complexity of the brain. So we transformed the approach of Massimini by looking at this type, not the TMS locked complexity, but complexity on the baseline. So it's not evoked by a stimulus, it's just the complexity of the signal before the stimulus comes. And what we have is a positive correlation in both wake and non-REM sleep. So in the parts of wake and sleep where they can do this task, we have a positive correlation. So the more the brain is complex, the more it can process a stimulus. In REM sleep, where we didn't see this ability to categorize stimuli, although they might be conscious, we find a reverse correlation. This time, the more they are complex, the less they can process information. And I think that's, this actually points to different mechanisms for responsiveness across sleep stages. In non-REM sleep, it will be neural stability, so the fact that the brain shifts its dynamic to a state where the balance of activation and inhibition is transformed. So this neuronal stability would prevent any ongoing processing. Stimuli are short-lived. They arrive at the cortex, but they don't propagate to other regions, limiting your ability to process information. In REM sleep, on the other hand, what could be limiting is not the ability of the brain of processing information, which it actually does, because we're able to dream. It's just that maybe these dreams, this endogenous process, are blocking the information from the outside because they are cornering cognitive resources. So we're, in a way, so immersed in the dream that we don't process external information, as in a state of maximal inattention. Another way of using sleep to explore consciousness is looking at all questions in the consciousness field, for example, relationship between consciousness and attention. That's something work we published recently about adapting the cocktail party problem during sleep. So our goal here was to see not only if sleepers can process external information, but if they can select which information to process. If they are exposed to different sources of information, will they preferentially process the source of the information that is relevant? And to use that, we had this experiment where participants were exposed to a meaningful speech and a meaningless one, and we reconstructed with their EEG what they were hearing. And we were comparing what they were hearing to the initial streams, and if what we reconstruct is closer to the meaningful stimuli, it means that they are paying attention to the meaningful stimulus. And what we have is actually, again, the similar kind of result. So obviously in wakefulness they can do that very well. In light sleep they can still preferentially process meaningful stimuli compared to meaningless one, but that's the capacity that disappears in deep sleep. Another interesting feature here of attention allocation during sleep was that contrary to wakefulness, it was transient. So in wakefulness, participants were able to focus on the stimuli for the entire length of the stimuli duration, which was 1 minute. In light non-REM sleep, this was possible only at the beginning of the stimulus, but not toward the end. As if the stimulus was someone waking them up, they could process this information, but then they were going back to sleep and ignoring it. So it seemed that with sleep we can map out both this level and how the contents are affected by the change of dynamics in different sleep states. It's interesting to see that the sleeping brain can process information complexly. So the sleeping brain is not a stupid brain in a way. It can still process a lot of information. Maybe it could be a tool to explore what is possible to process unconsciously. But the question is left open of why these processes are not reaching consciousness if they are occurring. And then another thing, and that's more closer to what we are interested in right now, is to try to see whether this level and content approaches are not quite artificial, and I think Tim will speak about it this afternoon, and trying to see how things are actually mixing up. Because for a very long time, sleep and wake were seen as two separate states. So you're either awake or asleep. But recent development in the sleep field showed that it actually can be quite intermingled. And you can have, when you're awake, part of your brain sleeping, and when you're asleep, part of your brain awake. So that has been first shown in animal studies, where with sleep-deprived rats, they show that the more these rats stay awake, the more they will show sleep-like patterns, like this regional interruption of firing that are reminiscent of sleep slow waves. And what they show is that not only does this happen, but it's associated with behavioral impairment. So if one of these local dawn states occur during wake in a region that is involved in the task, then it's usually associated with an error in the task. And this work has been replicated in humans, both in intracranial data, so that's the work I did with Yuval Nir, but also with scalp EEG with human participants playing Guitar Hero for 36 hours. Back in the day when Guitar Hero was a thing. So what we did with now was try to see if we could use this marker of local sleep to understand the dynamic of attention, and whether attentional lapses during the day could not be simply explained by problems of vigilance and parts of the brain falling asleep. So that's some ongoing development in the lab where we have people doing very boring tasks, so that's something I'm good at, making boring tasks. And we ask them from time to time what they have in mind. And we have more or less these three categories: either they're focusing on the task, or they are thinking about something else, so mind wandering, or they are mind blanking. So if you ask them, they cannot really report any thoughts going through their mind. What we have in terms of the proportion of these three states is quite typical for the literature. They are focusing on the task pretty much half a percent of the time. They are mind wandering pretty much a third of the time, and the remaining are instances of mind blanking, so they cannot really say if they were thinking about anything. What was interesting here is that the mind blanking seems associated by a lot of these local sleep markers, so these sleep-like waves that occur although you're awake. So just to be clear here, I mean, the participants are awake. They are well rested, they are doing a task, they are behaving. It's just that from time to time in their scalp EEG we can detect something that look a bit like a sleep slow wave. And when we do so, not only we can associate that with behavioral impairment, so when we see this slow wave, usually they are worse at the task, they make more errors, they are slower, but we can also map this with a phenomenology in a way. The more they have this slow wave, the more they appear to be in some sort of non-REM sleep, so they cannot really, at least you're waking them up, they cannot really say they were thinking about anything. And we can actually, looking at the amplitude rather than the number of this slow wave, we could actually differentiate this mind-wandering, mind-blanking state, so thinking about something or something else, or thinking about nothing. So this map shows the amplitude of this detected slow wave. So the diagonal is for the three states, and the triangle is for contrast between the states. So you can see that, generally speaking, the diagonal always shows the same topography. These waves are higher amplitude in frontal areas. But when you compare on and mind wandering, which is the top here, you can see that the waves we detect are the larger amplitudes in frontal areas. While when we compare mind blanking and on state, you can see that the larger amplitude waves are more in the back of the brain. So it seems that this local sleep do not only predict whether you will feel tired, be bad at the task, but also where they occur and the amplitude of this event can predict what kind of attentional lapses you will follow. What is the phenomenology associated with your lapses of attention? And in particular, whether you will start thinking about something else, or whether you will just think about nothing. And I think it's quite interesting to see that when you think about something else, it seems that your frontal cortex go off, but you still have awake parietal areas. So quite similar to this dreaming paper showing activation of the parietal cortex when people are dreaming. But when you are completely off, this time we see these slow waves having bigger amplitude in the back of the brain. So maybe this, again, fueled this debate of the frontal versus parietal importance of, for consciousness. So this is just a snapshot of this result. I mean, we have all very interesting other results, and I hope that we'll get them out as soon as possible. So to conclude this part, I think that sleep mechanisms are not only interested in sleep to understand how we sleep and how we process information during sleep, both exogenous and endogenous, but sleep mechanism could also explain during the day our ability to interact with their environment. And it is very possible that then the level and content approaches of consciousness cannot be fully orthogonalized, because it's very likely that during the day itself, I mean, your level of consciousness is not stable, but depends on the kind of content you're processing, and these contents themselves depend on your level of arousal and whether your brain is fully awake or entering this mixed sleep-wake state. So just as a reminder that, as usual, there's a lot of people behind this kind of work. So including my mentors. Now they are not supervisors anymore, they are mentors. So now Johan van Boxtel, now in Canberra, was involved in this study, and Jennifer Wint in philosophy. And then you have all the students who have been involved in these projects. Thanks.
It's very, very cool work. There's an old idea in sleep literature, you're probably aware of, I think due to Kleitman, where he proposed the basic rest activity cycle. And the basic idea of that was that the rhythms that happen when you're sleeping, your REM, non-REM, REM rhythms, extend through the waking day. In fact, referring back to the question I asked the last speaker about ultradian rhythms. So suppose there's a whole literature on 90-minute periodicities in cognitive performance, and it seems that your stuff is going to map very nicely onto that older literature. So can you comment on that?
Yeah, no, it's actually that's. I just wanted to show a figure when I presented this work last time at the sleep network. So that's basically my model, my working model so far. So very psychology-like model with boxes and so on, where indeed you will have this cyclicity in REM sleep that is under the control of neuromodulators, where you oscillate between non-REM and REM sleep, and this has a consequence in terms of your phenomenology, because in REM your dreams are frequent and rich, in non-REM they're infrequent and quite basic. And indeed, there's this whole body of literature showing that, well, suggesting that these cycles may be maintained during the day. And I think that these two processes that have been very well mapped in sleep, so the homeostatic process, so the build-up of fatigue, and the cyclic process, so determining sleep stages, maybe you will have similar things during the day. In the morning, you will be more sensitive to your circadian cycle, and maybe oscillating more between these periods of more intense mind-wandering or less intense mind-wandering. And the more you get tired during the day, the more mind blanking will become more and more prevalent, and your brain will suddenly switch off without letting much consciousness inside. To do this, we have planned that with people from the sleep and circadian team at Monash to try to do tasks during the day, both manipulating sleep and circadian rhythm, to try to see whether we have this kind of rhythm.
Very fine. Yeah, Martha?
Okay. So it's just relating to what you said, that towards the night we become more tired and have less awareness. But there are people who actually have this spike of activity, and if you're really energetic just before bed, my kids being like that. But so how do you reconcile that?
No, I'm pretty much like this as well. I wake up at 11 p.m. and then can be pretty efficient until 1. So that's actually well known. It's called the second wind. So usually it's designed biologically to happen in the middle of the afternoon to help us go throughout the end of the day. Probably with light exposure, it has been delayed. So now it happens at the wrong moment. So when we're supposed to go to bed. But that's something that is indeed known, and any kind of circadian research, or if we want to look into circadian effect, we'll have to take into account circadian profile. And it's very likely that we don't have, we might have individually consistent rhythm, but if you average everything, you might have something that flattens, which could be one of the reasons why this rhythm has been so difficult to evidence, is because maybe they're very personal and you need long time monitoring of individuals to have them appear.
Great talk. talk, Thomas. I've always wondered how we can be attentive during sleep. And the reason is, I've always wondered how we can wake up just before the alarm clock goes on. Even when the alarm time is set at different times. Do you know how that would work?
And so one of the, among the many things I would like to do, but time is limited unfortunately, is time perception during sleep and how we can monitor what time it is. Especially with this reported, this is reported often, this ability to wake up before the alarm clock, even when the alarm clock is not at its usual time. Or the ability to wake up more if something important is supposed to happen. That's called on-call sleep. So very well documented in medical doctors. And it's pretty much unknown what will happen. I think there will change of baseline. So if you know that you're likely to be woken up, maybe you just change your baseline level of neuromodulation, putting you closer to the wake-up threshold. And then there could be events that will more or less, once you're close to the threshold, help you cross the threshold more often because you know that something is going to happen. And in the recent paper we published actually on this attention task, we have something in this direction. So we looked at how the brain was responding to these sounds, and one of the ways to respond for the brain to external sounds is by producing a pattern activity that is called the K complex. So it's called the K of K complex stands for knock, because it was evidence when people were entering the room of patients sleeping, they would knock before, and they realized that when they were knocking, that actually these waves appearing on screen on the recording. So that's the one black trace on top. And these K complexes have been puzzling for sleep researchers because they seem both like a mechanism of protection of sleep, but also a mechanism of responsiveness to external events. What we show here is actually, so that's the stimulus reconstruction of the both meaningful in blue and meaningless in red streams. What we showed is that the immediate effect of this K complex is to kill the processing of both streams, so the protective mechanism. But what happened after the K complex is that not only you start processing the information again, but you start processing it in a way in a way close to wakefulness, because you're processing more the blue, meaningful stimulus rather than the red. And I think that is actually maybe one of these mechanisms of paying attention during sleep. You have these events that can kill off any sudden but isolated sounds, but if this initial sound is followed by other sounds, then you enter in a window in which you're more awake than usual, and you will be able to process that information. And neuromodulation could maybe change the probability that you will be able to produce these K complexes, and at a short-term time dynamic, this rhythm will allow you to build windows of alertness in your sleep, enabling you to monitor your environment. And the combination of two could explain why we have this ability to process our environment in a flexible way. So to process is when it matters, when we expect something or when something surprising happens.
I mean, that's very interesting, and I was thinking you could do a test of that hypothesis by taking those people who can wake up before their alarm and see if they have these K complexes.
Yeah, no,
but at face value, there isn't any other external stimulus, so it'd have to be purely endogenous.
It can be endogenous.
Okay.
Ariane?
I was posting the EEG activity and the difference between non-REM and REM sleep when people are reporting their when their dreams. I'm wondering if anyone's run the two-way crossover experiment where you have them doing that, you also have them like incorporating the external stimulus or not. So you have them during, like, are they dreaming, were they not dreaming, and then if they were dreaming, did they hear, like, did they incorporate the external stimulus or did they not incorporate the external stimulus? And then you could, like, with a two-way crossover, like, dissect out the different correlates.
Yeah, so that's that has been tried, I think, but I don't think there are anything published on this. The problem is incorporation. it's very rare to incorporate external stimuli into dreams. So it's quite difficult, and usually it leads to an awakening. So that's a classical thing of the alarm clock being transformed into a bell. Ultimately, it's waking you up. But usually, unless you use very strong stimuli, you can do pretty much, well, you can display tons of information during dreaming, and it's not much incorporated. That's actually quite close to the graph I shown on REM sleep on this task where they have to make left-right decisions. They're likely to be conscious. Their brain activity is very close to wakefulness, and still they are not able to process this basic information while they can when they are in non-REM sleep. So it's really seen that there is some form of blockade of information. It's just unclear for the moment how it happens.
Okay, so let me suggest close the session now, and because the lunch is already there, and some people may be already pretty hungry, so you can directly ask the question. So the original plan was to restart from 1:30, but shall we restart from 1:45? Yeah, because we started a little bit late as well. Okay.